Okay, so today's lesson is specifically on collecting like terms or just like terms in general. In order to talk about that, we do have to discuss sort of what a term is mathematically. It is the simplest of algebraic expressions, and once we've seen a few examples of what that might be, you'll probably get a bit of a better grasp on what a term could be. So a term, we've probably seen them before, could be numbers. So a number, which we basically call a constant, for example, the number 5 is constantly the number 5, or -3. That's another possible for a constant because -3 is always going to be -3. Or how about 3.14? That's also a constant because it's always going to be 3.14. So just basically a number. We could also use an alphabetical letter, and that could also represent a term. We use variables for those. So again, we've seen that before. X represents any number possible. Y could represent a different number from X, but any number possible. Y squared could also represent any number possible multiplied by itself. So you can do mathematical operations to those as well. We could also combine both of those concepts into one term because a product of a number and a variable, for example 2x, is also considered a term because 2 multiplied by x is the same thing as x multiplied by 2. They kind of come as a package deal together. If the term does include a variable and a number in front of it, we do call that a coefficient. So that number in front, the number 2 there in the second example, we call that a coefficient as well. So a polynomial is probably a word that you've heard of before. It's made up of a number of terms, so some terms together. Those terms get separated by a plus or a minus because when we're adding and subtracting those terms, they kind of get separated. Order matters when we're dealing with addition and subtraction, whereas with multiplication, order doesn't really matter. So some special polynomial names. If there's only one term, we'll call it a monomial or a monomial. If we've got two terms, we call it a binomial. And if we've got three terms, we call it a trinomial. And if we've got more than three terms, we actually just call it a polynomial after that. We just kind of get bored with it. So I've got three examples here. If you're interested, you can pause the video and think about all three of them before the answers pop up, or you can keep listening. The first one, for example, is a trinomial because as you can clearly see, there's a first term, a second term, and a third term. They're all separated by those addition or subtraction signs. So we've got a trinomial with three terms here. With B, we've got a monomial, because again, all of those terms are linked by multiplication, right? So there's no plus or minuses in between them all, basically just one term. With this very last example, we've got a binomial because those two terms are separated by the one subtraction sign there. So 10x is one of the terms and 1 is the other term. That's just some terminology, pun intended, that I'm going to be using for the rest of this unit. So like terms are terms that have the same variable that is raised to the same exponent. So a few examples here. For the first one, if I'm going to write a term that is like the following, that is like 8x, the term 5x would be like 8x because they're both dealing with the same variable, x, at the same exponent. Oppositely, 8y would not be a like term because it's got a different variable. It's got the same coefficient. It had an 8 in front of it, but it has a different variable. I want you to think about this as well, though. 5x squared. That also would fall into the category of not a like term because the x has been raised to the exponent of 2, whereas the x in the first case was raised to the exponent of 1. We just didn't really write it there, but it was raised to the exponent of 1. With example B, it's the same process. So again, we can change whatever coefficient we want, but the variable and the exponent have to stay the same. So you could write -7y squared, for example. You could write 23.2y squared. You could write anything y squared, and you'd be okay. With question C, here's a neat thing to consider, though, is that 2abc, you could write 5abc. And if you've been picking up on the pattern, -3.14 A, B, C would work as well. But I guess if you ponder some of the questions that are below, maybe we want to ask ourselves, what about 2BCA or 2CAB? Would that be a like term? Why or why not? So let's think about this. X squared y and xy squared, are they like? Why and why not? Well, think about it this way. Let's expand x squared y. What does it mean to say x squared y? Well, it means to take x, and it means to multiply it by x, and it means to multiply it by y. This other one over here means to take x and then multiply it by y, and then multiply the y by the y, because of BEDMAS we'd have to do that exponent first. You got to ask yourself, am I raising the same variable to the same exponent? Well, the answer is no. Right? X is being raised in the first case to the power of 2, and y is being raised in the second case to the power of 2. The last example, a squared b and b a squared. Well, let's think about this. The first one is a times b, and the second one is b times a times a. And if we look closely, we'll notice that there's an a times an a, which results in a squared, and an a times an a, which results in a squared. These are like terms. So to return to my example here with c, 5bca would also be a like term because we're dealing with the same variables raised to the same exponent. They're just presented in a different order, because b times c times a is exactly the same thing as a times b times c. It doesn't really matter. So to simplify these, to collect like terms, we can only add or subtract these like terms. It's kind of like their units of measurement. Okay, so what I would suggest for this first example, A, is that you actually deal with these brackets first, maybe reinterpreting subtracting a negative, maybe reinterpreting adding a negative. So what I'd ask you to do is to pause the video, maybe write these out on a scrap sheet of paper, and go ahead and consider some of the answers to these. The answers will pop up in just a moment, so pause your video now. Okay, so as you can clearly see, I decided to cover up a few things just to sort of guide our focus as we go. With the first example, you can clearly see that I'm subtracting a negative, and so I changed that subtracting a negative in this green step basically to just addition. And I do kind of the same thing with this adding a negative. That's the same thing as subtraction. So a good first step is to kind of clean up the brackets to just make it clear as to what we're adding or subtracting. Then, with my next step, I notice that I've got one term that has 3x to it. And you can see I underlined it in blue. And I've got to ask myself, like, do I have any other terms that are like the 3x? And as I look through at the line, I've got 5y, I've got 9, I've got minus 7y. I don't have any other x terms. So I basically just write that exact same term down. I move on to the next term, it's plus 5y, and I search the equation for another y term, and you can see it's color-coded. I underlined it in red. And I'm going to collect both of those. So I'm going to ask you basically, if you had 5 y's and you took away 7 y's, how many y's would you be left with? Well, you would be left with negative 2 y's because you had 5 and you took away 7. It's kind of like centimeters or meters or feet or apples or oranges. If I had 5 of them and I took away 7, I'd wind up with negative 2 of them. Finally, the constant, the plus 9, there aren't any constants for that plus 9 to get together with, so basically we just copy down the plus 9 itself, and there's our final answer. Same thing goes with question B. So with question B, you can see my first line I've done in black. I got rid of the brackets here for the subtracting a negative 1. So again, my main suggestion is, keep trying to follow BEDMAS, brackets first, right? So we want to get rid of that. We want to deal with that and clean it up a little bit. So subtracting a negative, same thing as adding. We then methodically go through the equation. As you can see, I underlined the 3y squared, and I looked throughout the whole equation for other y terms. You can see there's a minus 4y. If I have 3y squared and I take away 4y, I'm left with negative 1y. I color-coded it for you there. The second one, I've got minus 6y. Oh, there's plus 6y. So if I have negative 6 of something and I add 6, I wind up with actually 0 of that same thing. And finally, with the two constants, I've got plus 1 and I've got minus 3. If I have positive 1 and I take away 3, I wind up with negative 2. There's a little bit more cleaning that needs to go on here, though. Okay, so you'll notice that I have got negative 1 and I change that to just minus y squared. Well, that's the same thing, right? Because if I have negative 1y squared, well, that's kind of literally what I have here. I have negative 1y squared. So we don't have to write the ones in front of those terms. An interesting thing also happens with this plus 0y that's above. Well, if I have 0 y's, I don't even really need to mention it, do I? I mean, I have 0 x's as well. I have 0 t's as well, but you don't see me listing them, right? So there's no need to be listing that 0y. And the minus 2 there just continues from above because there were no other constants to deal with. All right, in example number C, really similar things are happening here, okay? So I start with the very first term, I search the equation, or the expression, sorry, for another term that's like it, and I collect them. Not forgetting that there should be actually a 1 in front of there. There's an imaginary 1. If I have two x's and I take away one of them, I'm just left with 1x. And you want to get into the habit of writing 1x like that without the 1 in front of it. The second term, again, I'm looking at negative 7y squared. And if I add y squared to that, I'm left with 6y squared. Now, actually, sorry, I forgot this 12y squared in the mix as well. So negative 7 plus 12 gives me positive 5, and positive 5 plus 1 gets me the positive 6 that I have in the bottom line here. Grabbing the pink highlighter for the red stuff, positive xy, and I'm taking away 1xy. So if I have 8 minus 1, I get positive 7. Again, the terms, or sorry, the variables on those terms are not going to change. Every single time, only the coefficient is changing because those variables are acting like units of measurement. If I have 8 centimeters and I take away 1 centimeter, I'm left with 7 centimeters. The units still stay the same. Now, an interesting thing, very interesting, happens with example D. Oh, you're already done. There are no like terms, okay? So if you're really looking closely and you're really paying attention, that example is quite easy too because there aren't any like terms to be collected. The 5x squared doesn't have any other x squareds. The x cubed, no other x cubes. The x squared y cubed, that's not like x cubed y squared, as I explained in the previous slide. Okay, I hope you enjoyed the quick lesson on collecting like terms. We'll see you in class tomorrow for any questions, and we'll run through a few more examples.